Okay, so welcome everyone to the 10th webinar of our BNP session. I have the pleasure of introducing Professor Peter Müller as today's speaker. Peter is a professor in the Department of Statistics and Data Sciences and in the Department of Mathematics at the University of Texas at Austin. His research interests focus on non-parametric Bayesian inference, Bayesian adaptive clinical trial design, Bayesian bioinformatics, optimal design and decision problems, and computational methods for Bayesian inference. The topic of his talk today is Bayesian non-parametric bivariate survival regression for current status data. Peter, thank you so much for accepting this invitation. And without further ado, please join me in welcoming Peter.
Thank you. Thank you, Felipe, for the chance to present here. I'm really honored and humbled. Compared to some of the outstanding talks earlier in this series, this is going to just be reasonably simple applied stuff. Actually, I kind of can tell you an executive summary just on the title slide. I want to tell you about data as it's summarized here on these two figures. On the left side, you can see 4 typical patients. We are talking about patients in a study where we record 2 event times. In this particular application, the 2 event times are time to infection and time to symptoms. These patients, the special feature of this data is that these patients only come once to the clinic. So at that moment, we can see the patients, and all what we get is we get 2 censored observations for the 2 event times, double censored, because let's start there with the left top. This patient who comes in at this time, C sub I is the time when the patient shows up in the clinic. We might see the patient does not have the symptoms, the patient does not have the infection. So all what we get is 2 right censored observations on the bivariate event time. In contrast, that patient here on the left bottom, that's a patient who comes in at time CI. And again, we get 2 censored observations, in this case, left censored, because this is a patient who has the infection and who has the symptoms. That patient on the, this patient on the right upper corner is kind of a bit funny, because this would be a patient who shows up at time C sub I, and we record a left censored observation on time to symptoms. In other words, the patient shows up with symptoms, but does not yet have the infection. We'll come back to that issue a bit later. So our data is bivariate data that's double censored on both sides, also known as current status data. So we have bivariate current status data, and we want to make inference about the underlying bivariate event time distribution. Before I get there, I'll talk briefly a few slides about univariate current status data. In this slide, you can see on the horizontal axis, you can see the actual censoring times, the C sub I on the left side of the slide. And the problem with current status data is well known. When you just do a non-parametric MLE, what happens is the probability mass for your estimated, these are survival functions, the probability mass for your estimated probability distribution piles up on either side of the range of the data, on either extreme side. You can see here the step function on the left that I follow with the cursor. That step function is the non-parametric MLE for this univariate current status data. Can you see there's the big step in the beginning and the big step in the end that corresponds to probability mass being shrunk towards the extremes of the range of the data. That's under non-parametric MLE, means not making any assumptions on the underlying distribution. And it's not an artifact of the discrete nature of the non-parametric MLE. If you replace it by a parametric model, say a mixture of 3 normals, all what happens is we get the smooth version of the step function, which just end up smoothing out the non-parametric MLE. But the basic problem of inappropriate shrinkage towards the extremes of the data range, that persists. Next thing we can do is when these patients come in with, when these patients develop symptoms, that quickly drives them to the clinic. Or in other words, the visit times, which function as the censoring times in our data, the visit times are obviously correlated with time to symptom, because when you get the symptom, that motivates you to come to the clinic. If we make use of this dependence between censoring times and event times, that greatly improves the non-parametric MLE. What you see here, like that gray step function in the middle, that's the non-parametric MLE, but using dependent censoring times that greatly addresses that inappropriate shrinkage towards the extremes of the data. And going then one step further and putting a proper prior probability model in the unknown distribution and introducing prior regularization, then we get the red estimate, that's the BNP estimate, and the black dashed line, this is a simulation study, the black dashed line was actually the truth. So this is almost too good to be true, yeah? Promise we didn't cheat, but it almost looks too good to be true. The BNP estimate actually in this case gets it almost perfectly. So all what I'll do in the next 40 minutes, I'll slowly talk you through these things. I think many of you could probably continue to talk from here. You can probably impute what's coming up. This is joint work with Giorgio Paolon, who is a PhD student here at UT Austin, just about to graduate, and Giancarlo Sali Rosas from Universidad Católica in Peru, in Lima. And I'll talk a little bit through the details. There was a URL on the title slide that ran off the slide. If you care for verbatim copies of my slides, they are available for download. Let me see if I can do that quickly. Felipe, probably it's easiest if I typed it. Let me see if I get the chat thing. I'll put in the chat box the URL of the slides. So this is www.ma.utexas.edu, users P. Müller, ISBA BNP.pdf. In the chat, you'll find the URL where you can download verbatim copies of the slides. So our data comes from a big study that enrolled some, I think it was like 1,800 patients. Those are patients who were treated for gonorrhea or chlamydia, and they were treated. So after treatment, they are symptom-free. There are two treatment arms. Either they just get the standard treatment, or they get standard treatment and some version of partner notification. And the question is whether that intervention changes the distribution of time to reinfection or time to recurrence of the disease. Our outcome is essentially time to recurrence, and we are reporting time to infection and time to symptom. However, both of them double censored by way of just recording current status data, because the way how the study is set up, after some time, these patients are supposed to come back for a visit, and just one single visit. And at that visit, we record whether or not they have the infection and whether or not they show the symptoms. So that's the setup of that study. Just quick summary of the data. Just want to draw your attention here maybe to the last line. The visit times, they're kind of all over the place. I think they were supposed to visit uniformly over a certain window, and that's exactly what we see in the visit times. They come like the median visit time is after 86, I think it's days, and in square brackets you see interquartile ranges. There's a wide range of times when they come back. We need some minimum of notation, not much. So on top of that slide, you can see like just for two typical patients, what it looks like. So the patient is initially disease-free because they get treatment. And as we progress over time, that gray line just indicates the time axis. As we progress over time, a typical red patient, at some time the patient gets the infection again, the disease recurs. And then the patient might at some random time come in for the clinic visit. For that red patient, for example, at the clinic visit, we would have a left-censored observation on infection and a right-censored observation on symptoms, because that patient comes in before the symptom shows up. However, it's also possible, like the purple patient, it's also possible that patients show the same symptoms, but due to different causes. Like the symptoms are general enough that they could also arise due to things unrelated to the infection of interest. So that purple patient might show the symptom at some time that might prompt the patient to actually come to the clinic. Now we get a left-censored observation on the symptom, and we might still get a right-censored observation on infection because the patient might not yet have the infection of interest. We might just record the symptoms due to other causes. So I already introduced here on the fly notation for time to infection, CAP-I-SAB-I, CAP-S-SAB-I, time to symptoms. So these are bivariate event times. The difference between S and I, that's just a latency time, like a lag time between infection and symptom that will feature in our upcoming model. C-SAB-I is the censoring time. In our actual study, it's physically the time when the patient visits the clinic. And the actual data that we get to record, we don't get to see the actual event times. We just get to see censoring indicators, delta CAP-I and delta CAP-S for the bivariate event times. And we have some basic covariates on each of the patients. Age, importantly, an indicator for treatment. That's actually the main inference target, and some more. Important to summarize the recorded data, the data that we condition on for the IF patient. What we get to see is we get to see the censoring time, the visit time, and we get to see the two censoring indicators for the two event times, and we get the covariates. Such data, like such double censored data, is known as current status data, and there's quite some literature on that. And what's coming up now in the next 40 minutes or so is I'll just briefly talk you through univariate current status data and the challenges there. I'll try to convince you to use a BNP model for prior regularization, and it also makes it natural to introduce dependent censoring times. And then we'll move to the bivariate model for bivariate outcomes, and don't expect any rocket science. It's going to be all reasonably straightforward, but the important thing is it works. I forgot to mention, I don't have those many slides and we are not that big a crowd. If you have any questions as we go along, please feel free to just unmute and ask. So let's first start just talking about univariate current status data when we just have one event time. Let's call it one event time CAP-S-SAB-I in anticipation of our application. Then all what we get to see is for each patient, we get to see a censoring indicator CAP-delta SAB-I. And without loss of generality, let's assume that we index the patient by appearance in the clinic. So the C-SAB-I are actually ordered. And without loss of generality, we'll assume that the first patient is a left-censored observation and the last patient is a right-censored observation. If it were different, same comments apply, it just changes the notation a little bit. The main comment here is you can easily show, if you jump to the last line on the slide, you can easily show that the non-parametric MLE means the probability measure that gives you the highest likelihood for such data if you don't impose any restrictions on the unknown probability measure. The non-parametric MLE is a discrete distribution with atoms at the following points. What we have to do is let's chase down, we should chase down all pairs of ones preceded by zeros. A pair of a one preceded by a zero, that would be a left-censored observation that follows a right-censored observation. So try to chase down all these red pairs of right-censored and left-censored observations. In this little cartoon here, I find 3 such pairs. So the 0 and 1, those are the observed censoring indicators CAP-delta. And then you can easily argue, you can very quickly convince yourself that the non-parametric MLE will only put, it will be discrete and will put probability masses only at the censoring times for these marked left censored observations. So the ones in each of these 0-1 pairs, they define the possible atoms. Plus there's one more last atom that's like just to the far right of everyone. Those are the only possible atoms for the non-parametric MLE. And that of course looks ugly. That looks super ugly because that's surely not what you expect the true distribution of the times to symptoms to be. It's highly implausible, just clinically or biologically. And on top of that, there's also this tendency for this non-parametric MLE. That left figure shows not a non-parametric MLE, the green pins, see those green pins. So the location of the pins, those would now be determined by these pairs 0-1. And the height of the pin, that's the probability mass that we allocate there. Can you see there's many pins here in between, but they get hardly any probability mass. Most of the probability mass for the non-parametric MLE is shrunk towards the extremes of the data. And this is actually identical to the picture that I showed you on the title slide. Just on the title slide, I showed you the same picture plotted as a survival function. For the survival function, the pins simply translated into the steps of the survival function. And you can see how we have this really implausible distribution with the probability mass on either side. It doesn't improve much when you replace the non-parametric MLE, that discrete distribution. That's obviously not a good estimate of the unknown time to symptom. If you replace it by a mixture of normal to smooth it out, it looks a little bit prettier, but it's nothing better because we still have all the probability mass on either extreme. So the blue line in the center that traces the MLE under the we constrained to the family of mixtures of normals. What looks like a decent sized bump here in between is not that big. It only looks like that because we indicate here like pointwise credible intervals. So it still has that same problem of allocating way too much probability mass, way too much relative to what is plausible or what you might deem probable by reasonable prior information, way too much towards the extremes of the data. We'll try to address that. We'll try to address that with two tricks. One trick is prior shrinkage that we easily get just by replacing the non-parametric MLE by posterior inference and the non-parametric base, which will simply mitigate the effect of shrinking too much to either side of the range of the data. And the other thing that we'll introduce is we'll introduce dependent censoring times. But you can see here what I just highlighted here in yellow is a specific model for dependent censoring times. Can you read the right-hand side of the definition as patients come to the clinic either after they get the symptoms, like if they get the symptoms at time SI, then after a reasonably short time that we assume to be exponential lambda, we assume that they show up in the clinic because they want treatment. Or they come by protocol. Protocol specified that they come in between, I think it was between 3 and 11 weeks after treatment, but they're supposed to show up in the clinic. And what we have there is a race between visit by protocol and visit by discomfort when they need treatment. So this is a fairly, still stylized, but fairly good representation of what's probably really going on to introduce informative censoring. Informative censoring helps a lot. This is back to our figure on the title slide. Can you see it's all again plotted as displayed as survival functions like 1 minus CDF. You can again see on the far left, you see those really ugly unrestricted non-parametric MLE. And then next to it, already much better, you can see the non-parametric MLE, but allowing for dependent censoring. So this is the non-parametric MLE, but now we include a factor in the likelihood for dependent censoring times using the yellow model there. And then going one step further, if we put the prior probability model on the unknown distribution, then we get the non-parametric Bayes inference, and that's the red survival curve on the right. And that's amazingly good for this data. I don't remember now by heart how many observations we had in that simulation study, but I think it was something like a couple hundred only. So a couple hundred double censored observations is not that much. And the non-parametric MLE still gets you like really awful inference, but prior shrinkage and informative censoring does the trick and gets you reasonable inference. And with that in mind, we can already move on to bivariate current status data. So this is back to our actual application. Recall that the data is just the two censoring indicators and the observed censoring time. The trick is that that censoring time is shared by the two endpoints. So we only get these censored observations that are aligned on the diagonal. Remember the title slide? We had these rectangles that were strung up on the diagonal. In particular, remember there was like one typical patient when you have left censored observation on infection and right censored observation on symptom. This could very well be a patient who gets the symptom due to the infection of interest. There was also this weird case of patients who have a left censored observation on symptom, but right censored on infection. That's the weird situation where the symptom shows up before the infection, and that is possible because those symptoms are reasonably generic in nature and you can have them for other reasons. And then there's two more cases. Thinking through these four possible cases, it's easy to write down the joint likelihood, and we're going to do that in a second. That's actually very informative to look at that likelihood, because then you immediately understand by inspection, you can see what's identifiable with such data. So I need some minimum notation. Let's note with F sub I, just the univariate CDF for infection. That would be the likelihood contribution of a left censored observation on infection. F sub S is the univariate CDF for time to symptom. So that would be the likelihood contribution of a left censored observation on symptom. And FIS, that's the likelihood contribution for a left censored bivariate observation on infection and symptom. So with this notation in place, it turns out we can write down the joint likelihood just using those three items. Which already highlights then the limitations of identifiability, because we can only learn about these three things. So we can identify the marginal distributions, but not the joint distribution, and that's the issue. So here's the likelihood function on top of this slide. Just a reminder again, our notation Fi, Fs, and Fis. Those are corresponding likelihood contributions for left censored infection, left censored symptom, and left censored infection and symptom. And with that in mind, you get the joint likelihood is a big product of all patients. The first factor is for patients who show up with both symptom and infection. The last factor is for patients who show up without symptom and without infection. And the other two factors are for the mixed cases. The important thing is you can actually write down the probability for all of them just using those three summaries, which immediately proves that the bivariate event time distribution is not likelihood identifiable. And noticing that the bivariate distribution is not likelihood identifiable, an obvious thing to do is to stitch together a bivariate event time distribution using univariate models. And stitching them together using a coupler, and it's exactly what some of the literature has done, Ma and others, Li and others, Wang and Ding. And that gives you a model for the joint for the bivariate event time distribution, where you have a hyperparameter in there, or you have one parameter in there that characterizes the correlation. Like if you use a Gaussian coupler, you just get like the correlation of the latent Gaussian. And then you do sensitivity analysis with respect to that assumption. That's totally sensible, and I think a very principled way to proceed. Paper by David Dunstan and Dinser, they actually proceed with Bayesian inference. They use probit models. They use probit models for independent distributions on the two event times, in our case, infection and symptom, and they introduce dependence by way of introducing frailties, and that also gets them dependent and informative censoring times. Reasonably straightforward and clean way to proceed. We'll do something similar, but exploiting more known structure of the problem. So we'll introduce structural assumptions that actually arise from this particular study. And on top of that, we have marginal models for infection and symptoms, and piecing that all together will give us useful inference on the bivariate event time. So the first assumption that we make is that the bivariate distribution on infection and symptom arises as a mixture. There's some patients, there's the yellow patients who show symptoms due to disease, and there's the gray patients who show the same symptoms due to other causes. Of course, this split into yellow and gray is purely hypothetical. We don't get to see it. One exception is if a patient shows up with infection before a symptom, then we know for sure that's a gray patient. So that first split just acknowledges that the symptoms are generic and could arise for other reasons. And we already introduced the constraint that in the yellow distribution, S has to be greater than I, because that's what we formulate. That's how we formalize the notion of symptom due to disease. And with that decomposition, we get the four likelihood factors. I remember 2 slides ago, we had the joint likelihood, which had like 4 different types of factors. And we can spell each of them out as this mixture. Where for the funny patients who show, there's something wrong in the caption of my table. This should be delta sub S. So for a patient who has a left-censored observation on symptom, but right-censored observation on infection, that can only be a gray patient. So that's the first step, to introduce some structure. At this moment, we have 2 unknown distributions, the gray one and the yellow one, and the additional parameter W. And this is back to the title slide, now showing you the likelihood contributions that arise from the gray one and the yellow one. Since under the yellow distribution, we have the order constraint, some of the rectangles actually just become like triangles, right, that are shown there in the yellow highlight. Next structure we introduce is for the gray distribution, for the gray patients. Now, if those are patients where the symptoms show up due to other causes, then it's reasonable to assume that in that case, symptoms and infection are independent. That's a massive simplification of our inference. So under the gray distribution, we just assume that the 2 event times are independent. That's another way of formalizing that these are symptoms due to other causes. And here the next one is a very useful one, but I think very sensible in this application. Under the yellow distribution, when the symptom is due to the disease, I mean, these are well-known diseases. A lot is known about how long it might take from infection until you develop symptoms. So we assume a parametric model for that latency time, where L is the time between infection and symptom. And we use in a parametric model, actually an exponential distribution with parameter lambda sub L. And we assume that the latency time is independent of time to infection, and that we introduced a massive helpful structure, because now we have characterized both of these bivariate distributions, the gray as well as the yellow, by underlying independence. In the yellow case, the independence is not on S and I, but it's on the latency time and I, but still allows us the same simplification. So now we are almost done. Can you see, I think the next slide, yeah, we can now spell out again the 4 factors in the joint likelihood. And now I plug in that additional structure that we introduced. Plugging in the additional structure that we introduced, you can see that all of them share the same marginal distribution for the infection, which either shows up as the survival function, if it's a right-censored observation on an infection, or it shows up as the CDF if it's a left-censored one. And for one of the factors, there's only the gray contribution. For the other factors, there's also a yellow part. For the yellow part, again, we can write it in terms of, see up there, you can write the yellow distribution for a symptom given infection before the visit time. You can write it as a appropriate summary of the assumed parametric form for the latency time, which has to be weighted with the time to infection, but that uses again the assumed distribution for time to infection. So in the end, all what we'll need when we specify our prior probability model, we'll need a prior probability model for the common F sub I, and we'll need a prior probability model for the gray marginal distribution of time to symptom, which is independent of time to infection for the gray patients. So we'll need prior probability models for 2 univariate event times. And probably many of you know more about that than me. And you can use your favorite distribution. That's exactly what we do. So we assume for the common time to infection, that's the red time to infection, we assume just a mixture of normals. For the gray time to symptom, we also assume a mixture of normals. And we complete in the usual BNP fashion, we complete our prior probability model with a BNP prior on the mixing measure, which is the H sub I and H sub S here in this notation. And really there you can use your favorite BNP prior. I don't think it makes much of a difference what you use. Like for univariate distributions, lots of alternatives. In particular, in our inference, we are not going to make use of any implied partition or random clustering. Like many times you might want to be careful which prior you choose if you actually want to interpret implicit clustering, but there's no notion of, there's no interest in this application. We're only interested in predictive inference. More importantly, we do want to introduce a regression on patient covariates because that was actually our main inference target. We want to see the effect of the treatment. In our case, the covariates are gender, age, and indicator for the treatment arm. The latter is what we are most interested in. So rather than a prior on the random mixing measures, the random mixing measures HI and HS is replaced by an entire family of HIX indexed with covariates. And there our favorite is the stupid but simple dependent Dirichlet process. And use your favorite alternative, absolutely no problem, yeah? You can use dependent Polier trees like Lorenzo Tripper had a nice paper on that a while ago. Whatever is your favorite model, you could use them. That's almost all that's to be said. Oh, we still have these 2 parametric submodels. I already introduced them on the fly when I talked about it. We use an exponential distribution for the regression of censoring times on symptom time for as a possibility. And we use an exponential distribution for the latency time between infection and symptom. Both of these, I think, are reasonable assumptions. If you replace them by alternative distributions, as long as the support of the distribution and the effective range and everything is the same, I don't think it would make much difference in our final inference. It's just important that you do introduce such regression. And having that, in principle, we can proceed with our inference. This figure shows you now our inference in the top row. You see on the left side is the gray distribution. That's the distribution, that's the estimated bivariate event time distribution for infection and symptom time for gray patients. The same for yellow patients. For yellow patients, the bivariate distribution is subject to an order constraint. So you can barely see that here. It's restricted to the upper diagonal. And we assume that exponential distribution for the, blah, 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 I misspoke. That's our inference on the gray distribution and the yellow distribution, and piecing them together, we get our inference on the unknown joint distribution of these bivariate event times. In a way, that's the first shot at solving this problem. At that moment, of course, you might wonder whether this is just prior in, prior out. Yeah, this might just be garbage in, garbage out, and we didn't learn anything. Just to convince you that this inference is actually driven by the data and the likelihood. On the next slide, I want to show you the. Want to show you the prior expectation. These are exactly the same figures for the prior expectation, quite different. So you can see how posterior updating, like introducing the likelihood, really informed our inference. It's still not obvious. Maybe like a lot of the features of our posterior inference could just be driven by our structural assumptions. To the extent to which these structural assumptions just reflect what is known about the study, that's totally appropriate, but you want to make sure it's nothing inappropriate. So in a moment, I'll show you some more simulation results. Before that, however, I advertised earlier, I promised you inference on a treatment effect. That's the main inference target here. And that was one of the reasons why we chose the DDP, why we chose the dependent Dirichlet process mixture, because that makes it very easy to tease out inference on a treatment effect. So we are using, in particular, we're just using a linearly dependent Dirichlet process, which you can also rewrite as so first of all, here's just again the mixture of normals with the H sub x. And under that simple version of the DDP, the H sub x just becomes a discrete distribution. Should really be a H sub x, yeah? That H sub x here. Here's the H sub x. The H sub x is a discrete distribution where the atoms of the discrete distribution, those are driven by a design vector corresponding to the covariance times just some linear model parameters, call it bold phase M. And all what the linear DDP really specifies is a discrete distribution on the bold phase M sub L. And for H sub x, you just pull out from that M sub L, you pull out the fitted value for a particular x, and that gives you then the H sub x. The important thing is under this model, there is a particular parameter in the M sub L can be attributed to the treatment because that M sub L, that would now be like an intercept plus an effect due to age plus an effect due to gender plus an effect due to treatment. And it's that effect due to treatment. So here the M is like alpha, beta, gamma for gender, treatment, and age. And it's the effective coefficient for the treatment indicator. That's what we are after. So we can actually talk about an H sub beta, which is just a discrete distribution on the treatment coefficients that is implied by this DDP. So same thing in a one-line summary. The DDP naturally implies a discrete distribution of treatment effects. And that's what we can show to display meaningful inference on a treatment effect. So in the next slide, I'll show you inference on the H sub beta. And that is our main thing to show for the treatment effect. So there are many things here. The main one, though, is this guy here. I can't make that. So this is the H sub beta. It's the implied inference on the distribution for the coefficients for the treatment indicator. And it's centered at 0, like here's the 0. So you can see this is actually with these 1,800 patients. It's many patients, but each patient gives you preciously little information. You just get this bivariate censoring indicator. Still in the end, at the end of the day, when all the smoke clears, you're getting quite informative posterior distribution on the treatment effect here. it's a bit funny that there's a positive effect of age. So actually, with increasing age, a positive effect is good because that means the time until recurrence, the time until infection is shifted to the right, right? There's a caveat to that. One caveat is that the patient population, if you watched slide 1 when I showed you a quick summary of the data, the patient population is overall very young. I think they're all like in their 20s or so. But you could interpret that maybe older patients are less likely to indulge in risky behavior. Maybe they're more cautious, more informed. Maybe old folks like us are simply wiser and smarter. Yeah? Down there, this is inference on the gray F sub S. So that is perhaps a little bit more difficult to interpret. One thing is comforting. Remember the gray F sub S, the way how it was set up, that is the distribution of time to symptom when the symptom is due to other causes. Where the due to other causes is, of course, just my arbitrary English tag for the thing. There was nothing in the probability model that really supports that interpretation, except I tried to build it accordingly. But it's good that the distribution of time to symptom, the treatment doesn't matter. The gray distribution of time to symptom, the treatment shouldn't matter. That's good, yeah? Blah, blah. You could go on to try to interpret it, but probably most would be over-interpretation. So there's one more thing I want to show you. With the posterior inference, so first of all, posterior updating, like adding the likelihood, really was informative. It changed our prior guess to posterior inference. I just noticed that my speaker turned off. If somebody said something in between, I did not hear you at all. I didn't mean to be rude. Either nobody is there anymore.
Nobody has said anything.
Thank you.
Yeah.
Thank you, Felipe. I just noticed, like, I have here an extra over smart setup, and I just noticed the speaker totally turned off. One time I was at a conference where it took the speaker like 20 minutes to figure out that he had lost internet. So just to demonstrate that inference is not only informative, but it is also meaningful. Here's a simulation study. The simulation study was set up in a way to mimic the setup of our actual application. In that simulation study, since we simulated, we play God, right? So we actually know the true infection times and the true symptom times. The white dots in this picture, those are the true times to infection and true times to disease. We didn't use the actual times as data. As data, we again just used the censored times. We just used the censoring indicators, like these pairs, delta I and delta S. We used that as data, and that is what we conditioned upon. And under the assumed model, the contours show you then again the inference on the unknown distribution on the basis of those bivariate censoring indicators only. And it's actually amazing how well that recovers the true distribution. Yeah, like if you see how well this estimated distribution traces the underlying event times that we don't get to see. Yeah, they're unknown to us. This is almost too good to be true. One reason why it is so good is, in this case, we actually simulated the data under the assumed analysis model. That always helps a little bit. Yeah, like most inference is really great under simulation, but real data is often wrong. Yeah. Anyway, this is just to make an argument that even for a finite sample size, similar to what we have in our actual study, you can reasonably well recover an unknown truth on the basis of just these bivariate censoring indicators. Giorgio carried out massively more simulations. So we have in the last column, there's like 3 different scenarios. In the last column, you see inference summaries under the proposed BNP model that we talked through in the last 40 minutes. And then you can also see inference under a completely parametric model and inference under independent BNP models. Part of what made our inference work, we think, part of what made this work were the structural assumptions on the dependent, like by introducing for dependent censoring, that was important. Introducing the parametric model for the latency time was important. If instead you just have two independent distributions, you get the summaries here in the first column, and the summaries that we report here for the simulation mean squared error for the unknown marginal distributions of time to infection and time to symptom. So smaller is better. And obviously there's selection sampling going on here. I would only show you the simulation if it looks good. But truly actually in these simulations, the structural BNP model that we proposed did reasonably well. By and large, we get the better results. And that is pretty much what I wanted to talk you through. So in summary, we introduced the BNP model for bivariate current status data. Importantly, we only needed BNP models for the marginal distributions. We made use of known structure in this study, and that really got us to a point where we can make reasonable inference with finite sample size and still hope to recover a meaningful truth. In a way, of course, BNP is always right, but in this particular case with current status data, if you don't introduce additional structure, you would still hit against limitations of identifiability. It was also important in this particular inference, it was important to anticipate the inference target in the model construction. Like in the end, if you want to have inference on a treatment effect, you better put some element in the model construction that you can then later interpret as a treatment effect. So in a way, I think of our whole construction as it's similar in spirit to coupler constructions because we start with marginal distributions and build a joint distribution. But rather than using a generic coupler, we used a construction that was really building on known structure in the problem. And that's all I wanted to tell you. Thank you.
Okay, so let's thank Peter for his presentation. So let me find the one.
Thank you.
Okay, so we still have some time for questions. So if you have any questions or comment for Peter, so just turn on the mic and go ahead, or just write your question in the chat. So by the way, there is a question in the chat. It was
sorry, let me see.
Luis Enrique, and he asks, don't you have problems when using normals for positive variables?
Quick answer, yes. Longer answer, it doesn't matter. We did actually try at one time, we tried to use log normals. Log normals is sometimes a bit awkward because it implies maybe a little bit too much skewness on the original absolute scale. So using normal kernels could become embarrassing if you start to predict negative times. But since we do have reasonably large sample size, we never ran into that problem. So quick answer, in general, you might have to be careful. It didn't cause problems for us. Yeah, good comment, good observation.
Okay, so any questions, comments?
They're all happy. They're all happy
Seems
with.
like...
I'm surprised they're all happy with the simple linear DDP because I know many have their favorite different prior models. But I think that general theme of building multivariate models for multivariate distributions by piecing together lower dimensional distributions with known structure, I think that's a promising one. But it's of course very problem specific because what is reasonable structure depends on the application.
Okay, so maybe I can ask a question, probably not a silly question. In slide 8, that was the slide when you mentioned identifiability. At that moment, you didn't have any predictors. So when you add predictors in this setup, do you need some additional considerations?
Good point. Cheap answer. If we just have like binary predictors like treatment and gender, then you simply have like 4 different subpopulations and the restrictions apply to each of the subpopulations, right? If you have a totally unrestricted model, if you introduce structure in a regression that links the submodels under different covariate combinations, then you start to borrow strength, and then I think you're kind of back to this setup.
Okay. So, well, if there is not any other questions for Peter, so let's thank again.
Thank you. Thanks everyone for joining.
Grazie.
Entertained. Thank you, Alessandra. Thanks for sneaking me into this series. You're the boss, right?
Well, not exactly. I'm